In exercise 944, we're doing a synthesis, and it's going to be a multi-step synthesis. It says, identify the reagents you would use to accomplish the following transformation. We're trying to turn this molecule and the other one. We need to know what recipe or recipes we're going to use. So first, try to see the similarities and the differences between the two molecules. Now in both of these, we have a 5-carbon chain. On the second carbon, we have a methyl group. And then on the fourth carbon, we have 2 methyl groups. So that's the same in both of the molecules. What's different? We have a bromine on the third carbon in the starting material, and we don't have that in the product. Well, if you start with something and you eliminate it from the molecule, then you're going to do an elimination reaction. So that gives us a clue of at least somewhere to start. We're going to do elimination. If we look at the other difference in the molecule, we can tell we don't have a bromine on the first carbon, the carbon on the left, in the reagent, but we do have that in the product. That means that what we're going to have to do is add that, so we're going to do an addition reaction also. We know that we'll have to do that at some point. Now we may have to do reactions in between those, but we know we at least have to do those. So we'll start with our starting material, the 2 methyl groups on carbon number 4 and 1 methyl group on carbon 2 here, and then the bromine. Okay, well, we want to do an elimination, and the truth is there's only one direction that we do the elimination in. And by the way, if you're thinking, okay, we know we have to do elimination or addition, how do you know which one to do first? Notice that for elimination, you need a leaving group, and we have one of those. For addition, you need a pi bond, and we don't have one of those. So we are going to do the elimination first. We have to use some sort of base, and you'll notice that the elimination product, there's only one of them. In order to do an elimination, you have to have a beta hydrogen. Well, the carbon that is attached to the leaving group, that's the alpha carbon, and each carbon next to that is the beta carbon. So we have 2 beta carbons, but we only have 1 beta hydrogen to the left. Notice the beta carbon to the right is bonded to 4 carbons. It doesn't have any hydrogens on it. So we don't have any hydrogens there, so we can't do an elimination in that direction, because the elimination happens when you have a base come by and steal that beta hydrogen. Those electrons go toward the leaving group and they kick the leaving group off. And so here you only get one product no matter what base you use. You could see that this is kind of a crowded area, though, so you might try to improve efficiency by using a skinny base like sodium hydroxide. You could also use sodium methoxide or sodium ethoxide. All of those would work. Any of those would work. I'm just going to use sodium hydroxide here. And what that would give you after that elimination reaction is a pi bond in the direction of the beta hydrogen that you stole, so to the left here. Okay, well, we're definitely a little closer than we were before. We got rid of the bromine that we knew had to go. So we did the elimination. Now, we know that we're going to have to do an addition. The problem is we want to add a bromine ultimately to carbon number 1 on this left side here. Over here, we want to add the bromine. But that is not one of the carbons in our double bond. So we want to sort of walk the electrons toward that carbon. In other words, we want, if you ever get stuck going in the forward direction for a synthesis, think about going backwards. Think about taking the product. So here we've gone forwards, and we sort of have a pi bond. We know that because we have that pi bond, the thing we can do with this is addition. We know that what we can do with this. In the big 3 categories we have of substitution, elimination, and addition, we don't have a leaving group, so we can't do substitution or elimination. We do have a pi bond, so we can do addition. So we know we have to do addition, but it may not be clear what we need to add. So let's say we got stuck there. One other thing you can do is look at the product and think, how could I have made this product? Now this is called retrosynthesis, because you're thinking going backwards. And the arrow that they use for this is not a regular arrow. That's what you use when you go forwards. the arrow is called a retrosynthetic arrow. It has sort of two lines and a bigger head, and that means I can make this from this other thing. That's what that arrow is saying. Now, what can you make that from if you're thinking about this from the perspective of retrosynthesis? Well, you can do an addition reaction. You can have a pi bond here. If you had a pi bond there, then you can add a Br and an implied H onto this double bond. So now, thinking backwards like that is a little bit useful because it lets us try to see a connection. We were here. We know the only thing we can do with this is an addition, and the next closest thing that will help us is getting here. So how can we make this? Well, that has a pi bond. The way you create pi bonds is through elimination. And so you can sort of see a connection. If we do an addition and we add a leaving group so that the leaving group is on this carbon, then we can do an elimination with that leaving group to walk the electrons over to the left. And it's this retrosynthesis that gave us some insight into that. So we're going to add a leaving group. Now, the leaving groups we know that are good leaving groups are the halogens. So how can we add a halogen onto this molecule? We don't want to add two halogens because we know that in our product, we don't have any halogens over here. So we just want to add one halogen that can function as a leaving group there. So the only reaction in all the addition reactions that we learned that adds one halogen is hydrohalogenation, so HBr. Now the other ones that add halogens are either halogenation, so you can use Br2, or halohydrin formation. That would be something like Br2 and H2O. But in that case, you'd have an OH on the molecule, and we clearly don't want that. So the choice here, the appropriate choice to get the halogen on, is hydrohalogenation. The question is, do we want Markovnikov addition or anti-Markovnikov addition? Should we add a peroxide to make the addition anti-Markovnikov? Okay, well, the carbon on the right is bonded to two carbons, and so that is secondary. The carbon on the left in the double bond is bonded to three carbons, and so that is tertiary. We want the leaving group to go on the more substituted carbon. This way, when we eliminate it, we can create a double bond further to the left. So we want the leaving group to go on carbon number 3. We want the bromine to go on carbon number 3. That means we want the hydrogen to go on the secondary carbon. So we want the hydrogen to go to the less substituted position. That means we want to do Markovnikov addition. And what that will give us, if we do Markovnikov addition with that, that means we don't add a peroxide, we just add HBr. In that case, we add the hydrogen onto that more substituted carbon, the less substituted carbon, and then the Br goes on the more substituted carbon. So that's the Markovnikov addition that you get there when you add just HBr without peroxides. Now I'm going to erase this hydrogen because it's implied in the skeletal structure. So now that we have another bromine, we can think of that as another leaving group. And we can walk the electrons, we can walk the reactivity of that molecule closer to the left of the molecule so that we can do an addition reaction. In other words, if you compare this structure with the ultimate structure we want, in this structure we have a bromine, and in the structure we want, we don't have a bromine on that second carbon there. So we have to do an elimination. Okay, well, how do you do an elimination? You treat it with some sort of a base. Now there are two different elimination products we could get here. We could either get an elimination where the double bond forms to the right, or we could get an elimination where the double bond forms to one of the methyl groups. Now notice both of these methyl groups are really symmetrical, and so if we do a double bond to either one, it's the same. So we could have this double bond going to the left and that's our other product. So these are the two possible elimination products that we could get from this molecule. Notice the one on the right is tri-substituted, and the one on the left is di-substituted. So the one on the left is the less substituted one, that's the Hofmann product, and the one on the right is the more substituted one, that's the Zaitsev product. Now we want the electrons to go to the left. We want them to go closer to the thing we're adding onto this molecule. So we want the Hofmann product. How do you get the Hofmann product? You use a bulky base. The bulky base you would want to be familiar with is potassium tert butoxide, TBUOK. And that looks like a tert butyl group that has an oxygen on it with a full negative charge. That's your base. That's stabilized by a potassium with a positive charge. So here's the tert butyl group, the oxygen, the potassium. So potassium tert butoxide is the name for that. And we are going to use that in order to get this Hofmann product. So we don't want the Zaitsev product. We do use a bulky base to get that less substituted Hofmann product. Okay, well, now if we compare this with the final product that we want, let me get rid of this stuff we've already taken care of, the bromine. I'll get rid of those yellow highlights. We can see this one last thing we need to add is this bromine here. So if you look at this molecule, we can see we have a pi bond. That means we're going to do addition, whatever else we're going to do. And what do we want to add? We want to add a bromine and a hydrogen. Right, there's no hydrogen here. We can see that in the product we want there is. So we want to add a bromine and a hydrogen to get this product. So that's the product that they have for us up here. Okay, well, to add a bromine or hydrogen, that's hydrohalogenation, so we do HBr. But is it Markovnikov addition or anti-Markovnikov addition? Should we add a peroxide or not? Here, the hydrogen is on a carbon that's bonded to 1, 2, 3 other carbons, so that's tertiary. The other carbon that was in the double bond, this one here, that was only bonded to one other carbon. And so that's primary. In other words, the hydrogen went on the more substituted carbon. That is anti-Markovnikov addition. To create anti-Markovnikov addition, you have to add a peroxide, ROOR, to that hydrohalogenation. And so that is your product. That's how you get your final product. So we sort of walked electrons over, and I'm going to erase this hydrogen because it's implied in the skeletal structure. But we sort of walked the electrons over. We saw when we compared the original structures that the carbon skeletons were the same. We had to eliminate a bromine. We know we had at least to do that, and we had to add another bromine in a different place. So there was only one way we could do the elimination, so we used a skinny base because it was kind of crowded there to accomplish that elimination, and that gave us only one elimination product. We had an alkene, we had a pi bond, so we knew the only thing we could do is addition. We wanted to do addition. When we did addition, we wanted to add a leaving group, because whatever we add, if you look at the final product, there's nothing there. So anything we add, we want to be able to remove it again. So we added a leaving group, a good leaving group, HBr. We did that so that we had Markovnikov addition, so that the bromine, the leaving group, got closer to where we ultimately want the bromine. We're sort of walking the electrons to the left side of the molecule. Now once we had that, we had a good leaving group, we could do an elimination again. We know we had to do an elimination because you see the bromine here, and it's not in the final molecule, so you have to eliminate it. So we knew we were going to use a base. We wanted to get the less substituted Hofmann product, so we used a bulky base, like potassium tert butoxide. Now we have the electrons all the way at the far left. You see this, you see the pi bond, you're like, okay, we're definitely going to do an addition reaction. What am I going to add? And you notice the bromine and the implied hydrogen in the product. That's HBr that you need to add, and it's anti-Markovnikov addition. The hydrogen ended up going to the more substituted carbon, so you had to add peroxides to get that anti-Markovnikov addition. So overall, what you need to make this process happen, the overall answer for this, the recipe, is first you need a skinny base like sodium hydroxide. Second, you would use HBr, that gives you Markovnikov addition of H and Br. Then you want to get the Hofmann product as the major product in an elimination reaction, so you use potassium tert butoxide. And finally, in a fourth step, you would add HBr yet again, but you want to add it anti-Markovnikov, so you do it in the presence of peroxides. And that altogether would be the recipe for that synthesis, for that transformation. If someone followed that recipe, they would make this transformation happen. So those are the reagents that you would need, that you would use to accomplish that transformation in exercise 944.